In this video, we're going to take a look at electrolytic cells. So electrolytic cells are based on a non-spontaneous redox reaction. So that means overall it has an E naught that is a negative value. And so in order to drive this reaction to go, because it's non-spontaneous, it requires an external power source, typically some kind of battery. And so what this is going to do is it's going to convert electrical energy back into chemical energy. So a typical setup here shows a cell where we put our electrolyte in. Now, an electrolyte can be a molten ionic salt. So molten just means in the liquid state. So that would mean molten. Or it could be a solution of an ionic salt. So that means water would be present as well. And so we have the solution, and then we have our two electrodes here. Now, electrodes can either be inert, which means they're non-reactive. So things like graphite, as well as platinum, can be non-reactive, or they could be reactive types, so they might be some sort of metal. And so we might need to consider them in the reaction as well. And the electrons, as always, they're going to flow from anode to the cathode. So that's the same in any electrochemical cell. But now the electron flow is being dictated by the DC power source. So it's being dictated by the fact that our battery is pushing those electrons through in that particular direction. So we have a positive charge at the anode then, and a negative charge at the cathode, and that is just solely based on the charge of our battery. Oxidation always happens at the anode, and so we're going to have electron loss there, and reduction always happens at the cathode, so we'll have electron gain there. So that doesn't change between electrochemical cells. So let's look at a couple of examples. So we're going to look at the electrolysis of molten sodium chloride with inert electrodes. So what that means is we have sodium ions and we have chloride ions in our electrolyte, and that's all we are considering here. So when we kind of take a look at those redox potentials for those particular things, let's find chlorine down here, and our sodium is up here. So that means that the Na plus is our strongest oxidizing agent, and our Cl minus is our strongest reducing agent. So the Na plus is going to undergo strongest oxidizing agent, so it's going to undergo reduction, and reduction happens at the cathode. So let's put that in here. So this is our cathode reduction. And then at our anode, we're having chlorine ions becoming Cl2. So maybe let's balance it so we can get rid of that half. So we're creating chlorine gas at our anode where oxidation is taking place. Okay, and we would have a positive charge here and a negative charge here. So this is a really nice process because it allows us to take a molten solution of sodium chloride and basically get its elements out of it. So this is a way that we can refine different materials to get the source elements back out of it. Now, if we do electrolysis with aqueous solutions, we have to kind of keep in mind that redox reactions involving water are going to compete with the redox reactions of the ionic salt. And there's two places where water shows up here. First is down here as a potential reducing agent. And then the other one is up here where it's a potential oxidizing agent. So important to kind of take a look and see which one is your strongest oxidizing agent, which one's your strongest reducing agent, and that's going to help you figure out what is happening in a particular electrolytic cell. So let's take a look at an example of an aqueous solution. So we got aqueous sodium chloride. So we have to consider sodium ions, we have to consider water, and we have to consider the chloride ions. So let's find these in our tables. So sodium's up here. our water on our this side, on the oxidizing agent side, is here. And then if we look at the other two, we got water down here and chloride down here. Now, the case between sodium and water for the strongest oxidizing agent is pretty clear cut because the E0 values are quite different from each other, and the water is most certainly the strongest oxidizing agent. So at the cathode then, that's going to undergo reduction. So we are creating hydrogen gas at the cathode. Okay, so that's reduction happening there. So you would see little bubbles of hydrogen gas coming off of this electrode. For the anode, it's a little bit trickier because the E0 values are so close together. So you got 1.23 and 1.36. So they're a lot closer together. It's not as clear-cut of an answer at this particular anode. And so what's going to happen if you had really high concentrations of sodium chloride in here, so high concentrations of chloride ions, then chlorine gas is going to be our main product. So we're going to be forming Cl minus going to have Cl2 and an electron. But if we have more dilute solutions, then you get a mixture of the chlorine gas and the oxygen gas. And then if you have very dilute solutions, then primarily you're creating just oxygen gas at the anode. So it's not as clear cut just because those E0 values are very, very close. And so it's going to be dependent on the concentration of the chloride ions in the solution. Now, taking a look at another example here, we have aqueous copper 2 sulfate. So let's find those reactions again. So we've got water here and copper 2 plus here. I know it's here as well, but this one's lower anyway, so I'm not even going to bother highlighting that one. And then on the other side, we have water, and that's pretty much it because the sulfate's right here as well. So if you take a look at the reactions we're considering here, so let me just quickly write down, we've got copper 2 plus ions here, we got sulfate ions, and we've got water to consider. If we're looking on the strongest reducing agent side, the only thing we're considering here is our water. And so that is our strongest reducing agent. So it means that's going to undergo oxidation. So we're going to have water giving oxygen gas, 2 H pluses, and 2 electrons. So we're going to get little bubbles of oxygen gas produced at the anode. Now at the cathode, considering our reactions, our copper 2 plus is our strongest oxidizing agent. And so that is the one that's going to undergo reduction. So we're going to create solid copper here. Okay, this one's fairly more clear cut in terms of the reaction. And what's really neat about this is eventually copper 2 sulfate is blue in color. The blue is coming from the copper 2 ions, but as they get used up, as they create solid copper, and as they're replaced with hydrogen ions, the blue color in this solution is going to fade. Now, a really neat application of electrolysis or electrolytic cells is electroplating. And so what we do is we use electrodes made from a reactive metal rather than inert electrodes, and that's going to add material to the cathode, and that's called plating. So this example here, we've got a spoon at our cathode. Our cathode is undergoing reduction, and so we're getting, in this particular reaction, silver ions are being plated as solid silver onto this particular spoon. And then as we're doing it, we have also a silver anode here, and that is eroding that material from there. So essentially, we're transferring the silver from this one electrode onto the other electrode. So if we go back to our example now of aqueous copper 2 sulfate, but with copper electrodes, we have to consider our solid copper in here too. Okay, so we would have our water and our solid copper. Then we would also have our sulfate ions. We have this reaction as well. And then we also have our water up here. So if we took a look at our, for our strongest, let's go, whoops, no, that's reduction. Okay, anodes oxidation. Let's put our battery in there. Now let's look first for our strongest oxidizing agent because that is going to undergo reduction. So we're looking at considering copper 2+, the sulfate, and the water. So copper 2+ is our strongest oxidizing agent, so that is what is undergoing reduction. And then we're considering our solid copper on this side now for our strongest reducing agent as well, because we do have that in the mix now. So if we look between water and copper solid, our copper solid is our strongest reducing agent, so that's going to undergo oxidation at our anode. And so what you'll end up seeing as you're observing this reaction is that the blue color is not going to fade if we have copper electrodes, because we're replacing the amount of copper 2 ions in the solution, and so we're keeping it constant. But what you would see is that the mass of the anode would decrease and the mass of the cathode would increase. So really kind of neat application of electrolysis and electrolytic cells. So that's electrolysis, all of the different kinds of combinations we might see. That's it for this video. We'll see you in the next one.